So in Unit 13, we're going to start our discussion with reaction times. And reaction time is defined to be the interval of time between application of a stimulus and detection of a response. So athletes are often concerned with the reaction time. What are some situations in everyday life where reaction time is important? So, of course, in athletics, we'll go ahead and put that down. That's one of those. So, you know, how fast you can hit or throw or start. You know, when they have a picture here of a track meet. One of the biggest things with running is being able to get out of the blocks quickly. Same thing with swimming, any sort of a race. You're going to want to be able to get off the blocks quickly. So there's lots of things in athletics, but what are some things in everyday life, things that you do every day? When I pose this to students in my classes, they usually have a pretty hard time with this because they're so used to thinking of reaction time as being an athletic thing when you're playing a sport. But we actually use reaction time all the time. One thing that students do usually come up with is driving. Of course, if someone pulls out in front of you or veers into you, you might need to slam on the brakes, you might need to speed up, you might need to swerve. There's all kinds of different things in driving that require a reaction time, but there's even some really simple things. Like even just when you're walking and you maybe drop your foot off the edge of the sidewalk or you step off a curb that you didn't mean to. So when you're walking and you need to keep yourself from falling, maybe you slip on the steps or something like that. But any of those times where you have to catch yourself and keep yourself from falling or keep from dropping something. You have something in your hand. Something we're all familiar with is our phones. You have your phone in your hand and it starts to slip. Do you have the reaction time to grab it or not drop it? You know, grab it after it falls or not drop it out of your hand. One that does come up when we start talking about the everyday things is the times that maybe a child starts to fall or a child does something. So to, you know, keep a child from harm. If you've never seen it, there's some pretty funny videos on YouTube about dads. The one I saw was specifically dads. I'm sure there's ones with moms also, but it was like times that dads kept their kids from getting hurt that were just kind of miraculous, how quickly they could react and get under the kid or grab the kid to keep them from falling or having something hit them. So these are all reaction time. Reaction time is the interval of time, how long it takes you from the application of a stimulus. So a stimulus in athletics, if you're hitting something, say in baseball, the stimulus would be the pitcher throwing the ball coming towards you, and you decide now's when I need to hit. How long does that reaction time take? You pick up a ball, you need to throw it, you need to shoot it. How long does that take? The gun goes off or the starting buzzer goes off in a race. How long does it take you to actually get started? Driving, how long does it take you to swerve or brake or accelerate to avoid some hazard? How long does it keep you to keep yourself from falling or dropping something or get underneath a child or catch a child? All of those are reaction times. So what we do in class typically is we do this testing of reaction times, and each person in the class will do this. And what you do is one person holds a ruler vertically, so up and down, and then another person holds their thumb and first finger about 1 inch apart, and at the bottom of the ruler. And the first person tries to drop the ruler while the second person tries to catch it. I am not a good artist, but I'm going to try to draw you just like an example of what it is. So like this would be the ruler, and you'd hold it so that like this would be 0, and this would be like 1, 2, and so on. And then the other person puts their hand, I'm not going to be able to draw this, puts their hand here with their fingers apart, and then they try to grab the ruler. Oh my gosh, this is supposed to be like a thumb and a first finger. So you have your arm out here, and this person tries to pinch the ruler as the other person drops it. And however far up the ruler you get, that's what you mark. So what I did, since we don't have our class to do it, is I just did it for myself, and I had my son help me, and these are the distances that I measured for my reaction time. We're meant to do it 6 times, and then we're meant to do the average. So we're going to do 9.5. To get an average, we're going to add them all up and divide by how many there are. So 9.5 plus 8 plus 7 plus 10 plus 7 plus 7.5. That gets me 49. And if I take 49 and I divide it by 6, I get approximately 8.17. I'm just going to do 8.2. So my average is about 8.2 inches. Now I have a formula here that's supposed to calculate your reaction time, like how many seconds did it take you to react. The only problem is this formula gives us D to be the average distance in feet and T the time in seconds. Well, we don't have our average distance in feet, we have it in inches. So what we need to do is convert that. So 8.2 inches divided by 12 inches per foot. So 8.2 divided by 12, since there's 12 inches in a foot, and we'll figure out how much of a foot that is. 8 out of 12 feet would be like 2/3. So it's going to be a little bit more than that. 8.2 divided by 12, we get about 0.68 feet. So that's the number that we're going to use up here. So my average is over half a foot, which makes sense because everything was over 6 inches, and 6 inches would be half a foot, but not more than a foot. Again, that's obvious because I don't have anything that's 12 inches. They're all between 6 inches and 12 inches. So the fact that it's over half of a foot, but not as much as 1 foot, makes sense. So I'm going to go over here. I'm going to calculate my average reaction time. T is my time, and D is my distance. So that's the 0.68. It says it has to be the distance in feet. So 0.68 feet. And then I'm going to divide that by 15 feet per square inch. Don't worry about this. This is just a unit, not per square inch, per square second. This is just a unit. You don't have to do anything with that square. That's just per square second. This is based on the how quickly gravity pulls you to the ground. And it's an acceleration because you go faster as you go close, as you fall more. So this is 16 feet per square second. But we don't have to do anything with these units. The feet are going to cancel. The square root is going to take care of the square on the seconds, and that's all going to be taken care of, and we're just going to get seconds out. So that's all taken care of with the formula. All we have to do is calculate this. So on your calculator, what you want to do is you want to do 0.68 and divide that by 16. And you're going to get an answer. And I would suggest you practice this here while I'm doing it. So 0.68 divided by 16, it comes out to be 0.0425. And what I would do if this didn't come out nicely is I would just leave it in the calculator and not try to round it. I would just leave whatever was in the calculator. I might write down an approximation, but I wouldn't take the number out of the calculator. So now T is going to be the square root of 0.0425. And so if we do square root 0.0425, I get approximately 0.206 seconds, believe it or not. So my reaction time You know, you might think, oh my gosh, I got 10, that's horrible, or I got 9.5, that's horrible. Even if you had 12, that's a fraction of a second. And most anybody can catch, you know, unless they have some sort of issue going on with their reaction time, most people can grab a ruler in less than 12 inches. So at my average of 8.2 inches, that means that my reaction time for these 6 trials on average was 0.206 of a second. So about a fifth of a second before I could grab that, which is, the human body is just remarkable. I'm just a middle-aged woman, not an athlete, and that's my reaction time. So let's go on to section 13b. So now we're going to look at breaking down a formula. And what they mean by breaking down a formula is looking at a formula and trying to figure out what each of the different variables within the formula does, how they affect the formula. And we're going to look at this formula that looks kind of scary at first, but don't panic. This is a formula for D, which is the braking distance of a vehicle, where V sub O, this is all one variable. I know it looks like this 0 or this O would be a variable, but it's not. It's actually part of this V, and it means the initial velocity. The 0 can represent original, or it can represent like time 0, like at the beginning. So sometimes you'll hear this pronounced initial velocity. Sometimes people will say V naught or V sub 0, and this square does apply to the V. So whatever the V naught is, then we're going to square it. At the bottom here, then, we have 2 times G, and there's a little g and a big G in this formula, so you can't use them indiscriminately. You have to differentiate that there's a little g and a big G, and the little g is actually a constant, so we're going to put in the same number every time for this. We're going to work in feet per square second most of the time. I think there might be one time they ask you to do meters per square second, but this constant 32.2 is due to gravity. So that's the acceleration due to gravity, and it's not going to change because that's a force that remains consistent throughout the entire Earth. It does vary the tiniest bit depending on some things, but for the most part it remains 32.2 fairly consistently around the Earth. The F is what's known as the coefficient of friction between the tires in the roadway, and it goes anywhere from 0 to 1. So 1 would be like so much friction you can't move, and 0 would be like no friction at all, completely slippery. The G is the roadway grade, and it's a percent in decimal form, and it's like the slope of the roadway. If you have a positive grade, that means that you're going upward, and if you have a negative grade, that means you're going downward. So you could have a positive grade, which is like going uphill, slowing your vehicle down as you go uphill, or a negative grade would be going downhill. If you've had some algebra, that kind of relates to the fact that if you have a positive slope, that would go upward, and if you had a negative slope, that would be going downward for the slope of a line. So positive means you're going uphill, and negative means you're going downhill. So we're going to look at the relationship between the variables, and what it says is we're going to understand this, we're going to hold 2 of them fixed. Now what they mean by hold 2 of them fixed means we're going to put a number in for 2 of these variables and not change them, and only change the other variables. So there's actually, and if you go up here, there's 1, 2, 3, 4, 5 variables, but remember G is a constant that we're going to replace. D is what we're trying to solve for. So that leaves, you know, these 3 variables over here that can change, and this one that can change. And so we're going to hold F and G fixed. So this is going to get replaced with a constant. We're going to put in a number for f and g, and we're going to change the other variables and see how they affect each other. So it says, consider a situation in which the coefficient of friction is 0.8 and the roadway grade is 0.05. Write a simplified form of the formula using these variables. So I'm going to first write the formula down as they had it. So V naught squared over 2 little g F plus G. So in this case, D is going to equal V naught squared over 2 times 32. I'm going to go back here so you can see this. Remember, this was a constant. It said that that's always 32.2 feet per square inch, or feet per square second. And so we're going to put in 32.2 here. And then we're going to multiply that times F plus G, but it's telling us that they want us to hold F, the coefficient of friction, as 0.8 and the roadway grade as 0.05. So this is 0.8, and then we're going to add that to the roadway grade of 0.05. So 2 times 32.2 times whatever the sum of this is. So they want us to simplify that. It says write a simplified formula using these values. So if these are all going to stay the same, we don't have to keep computing it over and over again. We can just say, I don't need the D again, just a second. We can just say that that's equal to V naught squared over 2 times 32.2. You should have a parentheses on your calculator. If you just push the parentheses, you shouldn't even need to put the multiplication sign because it should know that. So 0.8 plus 0.05. So try typing that in your calculator right now. See what you get, and then we'll match up. So I got 54.74. So this is the simplified formula, given that those things are going to remain constant. So V naught squared over 54.74. And that's our answer for number 2. Now it says calculate the braking distance when the speed is 45 miles per hour, or 66 feet per second. How does this distance compare to the prediction we made in question 1? So let's go back and look at V naught. And it says it is the initial velocity of the car in feet per second. So when I put this into the formula, I don't want to put it in as the 45 miles per hour. I want to put it in as the feet per second because that's how the formula is set up. So I'm going to use, before we calculated that 45 miles per hour is the same as 66 feet per second. So for 45 miles per hour, I would do 66. That's my V naught, my initial velocity, my starting velocity. I'm going to square that, and I'm going to divide that by 54.74. Again, pause for just a second, calculate this and see what you get, and then see if it matches up with what I have. So if I calculate this, 66 squared divided by 54.74, and I get approximately 79.6. It comes out to be 79.5761783. But if I want to round to one place past the decimal, it's 0.57, so the 7 is going to round the 5 up to 6. So 79.6. And that's the distance. Remember, this is feet. This is the distance it's going to take you to stop if you are going 45 miles per hour. And we were supposed to make a prediction over here, and I kind of jumped ahead. But we were talking in the prior lesson about how far you'll travel in 4 seconds. That's not applying that brake. That's just saying if you're going 45 miles an hour, how far do you go in 4 seconds? What we're doing is we're predicting the braking distance that the car will travel after the brakes have been applied. So if you push on the brakes going 45 miles per hour, as long as your gravity and your sorry, I lost where I was at here. As long as the friction is that 0.8 that they're talking about, and the road grade is 0.05, which means you're slightly going uphill, then it would take you just under 80 feet to stop. Remember, that is, we talked about the length or the width of a lot of classrooms is about 30, so that'd be like more than 2 classroom lengths, 2 plus classroom lengths before you could stop. One of those things that a lot of people think is a lot shorter than what it actually is. Now it says calculate the braking distance when the speed is 45 miles per hour. We did that already, sorry. This was 2. And this was actually 3. Let me fix that so you're not confused. So this was actually 3. And we're ready for 4. When the speed is 45 miles per hour, 66 feet per second, calculate the braking distance at the roadway when the roadway grade is 0.15 and 0.30. So now what we're going to do is we're going to go back to this formula, and instead of having the roadway grade be 0.05, we're going to have it be higher at 0.15 and then even higher at 0.30. Remember, this means that you're going uphill. So say 0.05 is just a tiniest bit upward. 0.15 would be a little bit more slanted, and then 0.30 would be even more slanted than that. So I don't know if this is not perfectly correct, but you know, say 0.15 would be a little bit more slanted. Try that one more time. And then 0.30 would be even more slanted than that. So we're talking about getting steeper with these numbers. So what's going to happen before we even calculate this? If the road is getting steeper, you're going uphill, is that going to make you stop more quickly or more slowly? Or is it going to take you further to stop or shorter to stop? Well, if you're going more uphill, it should take you less distance to stop because that uphill is keeping you from accelerating. So as we put these numbers in, as we go from 0.05 to 0.15 to 0.30, it should take us less distance to stop because we're going more uphill. So let's calculate that for these. So for 0.15 for G, we're going to get that the distance equals 66 squared. That's the 66 feet per second speed at 45 miles an hour. And then underneath we're going to have to kind of recalculate. We still have the 2 and the 32.2, and we still have 0.8, but now the other G is going to be 0.15. So what does that give us? That'd be 66 squared over 2 times 32.2, and I could have actually put that in as 64.4 if I wanted to, because that's what it comes out to be. So 2 times 32.2 times parentheses, don't forget to do the parentheses, 0.8 plus 0.15. And yes, you will get a different answer if you don't do the parentheses. And this bottom number comes out to be 61.18. So 66 squared divided by 61.18 gets you a stopping distance of about 71.2 feet. So it doesn't save you a lot of distance, but it does cut it down by, what is that, 8.4, so almost 8.5 feet. And then if we change the roadway grade to 0.3, we're going to do 66 squared over, I'm going to go ahead and write this part right here as 64.4. 64.4 times 0.8 plus 0.3, which would give us 66 squared over 64.4 times parentheses 0.8 plus 0.3, close that parentheses up, and you should get 70.84. You notice we're getting a larger and larger number, 54.74, 61.818, and then 70.84. So that bigger number on the bottom means it's not going to divide in as many times, and we're going to get less distance. So 66 squared divided by 70.84, we get 61.5 approximately. It's 61.490, so 61.5 feet. So that's what we needed to calculate for this lesson, and we're going to just kind of continue with this pattern as we get into C and D. So now we're going to continue with this same formula that we had before, and we are going to fill in some different information. Before we do that, I'm going to go ahead and write down what the formula was. Remember, we had the formula D equals where am I at here? D equals V naught squared over 2G times F plus G. But we noted that this G, this small g, is going to be a constant, 32.2. And so we'll rewrite it with that. So V naught, that's initial velocity, squared, divided by 2 times 32.2 would be 64.4, and then F plus G. So even though it looks when we start like we have 5 variables, we really only have distance, initial velocity, friction, and, whoops, I wrote that wrong, friction and the grade. But the grade is supposed to be a large G. So it says here at the beginning of the lesson, we predicted, of lesson 13b, we predicted the stopping distance when the speed was 45. Were you surprised, or was your prediction fairly accurate? What if the speed was different? So we had calculated the stopping distance when the F was 0.8 and the G was 0.05. We had calculated that the stopping distance with a velocity of 45 miles per hour, which was 66 feet per second, to be about 79.6 feet. And that's with initial velocity of 45 miles per hour, which we put in as 66 feet per second, F of 0.8, and G of 0.05. So the question is, how could you explore the effect that different speeds have on braking distance? And they say here, but this is actually basically almost answering our question, we're going to keep the friction and the grade fixed, and if we want to see the effect different speeds have, we just need to pick some different speeds, because the whole bottom is going to be relegated to a constant if we hold the F and the G the same. So we're going to figure out the distance if our bottom is 64.4, and then our F is 0.8, and our G is 0.05. And we're going to put in some different velocities and see what we get for distance. So this bottom number overall simplified just like before. I can't remember what it was, 64.4 times parentheses 0.8 plus 0.05, which you could put in as just 0.85. And that would be that 54.74 that we had before. So now let's look at some different velocities. So let's say instead of going, I'm going to pick some easier numbers here. Instead of going 66 feet per second, let's go a little slower. let's say that you're going 50 feet per second. And we'll say this is in feet. All of these is feet per second. So say you're going 50 feet per second, what would that give you for a distance? Well, we're going to take this number, we're going to plug in a 50 right here, and we're going to calculate it. So we're going to do 50 squared divided by 54.74. So 50 squared divided by 54.74 gets us a distance, as we would expect, since we're going a little bit slower than 66 feet per second, we're going to take less time to stop. So it's only going to take us 45.7 feet rather than 79.6 feet. So when we drop our speed by 15 feet per second from 66 to 50, or 16 feet per second, we're going to drop our stopping distance to 45.7. So now let's look at some numbers that are kind of easy in comparison to 50, because here in a minute it's going to talk about doubling and tripling speed. So let's look at what happens when we go to 100. Again, this number goes in up on top. So that's 100 squared, which is 10,000, and then divide that by 54.74, and you get that the stopping distance is about 183.7 approximately. So we doubled the speed, and this is what happened to the distance. Now let's look at, say, 150 and 200. And this is 100 feet per second, 150 feet per second, 200 feet per second. So 150, we're going to put that here for velocity, 150 squared, and then divide that by 54.74, and you get about 411 point, it's actually 0.0 if I round it correctly, but I'll put the 0.0 since all these were rounded to the 10th. So we went in 50, adding another 50 feet per second on, this is what happened. Adding another 50 feet per second on, this is what happened. If we go to 200, 200 squared is 40,000, and then divide that by 54.74, and you have about 730.7 feet. So what's happening here is that as the speed goes up, 50 feet per second, 100 feet per second, 150, 200, the distance is clearly going up. But is it going up if we double the speed? Does that double the stopping distance is the question that we're going to talk about here. So if we go from 50 to 100, we've multiplied by 2 the speed. So how do 183 and 45.7 compare? Well, this is clearly not just double. Double would be a little over 90. So let's take 183.7, and we're going to divide that by 45.7, and we're going to get, there's been some rounding involved, but essentially what happened here is it got multiplied by 4. This stopping distance got quadrupled rather than just doubled. Now let's look at another one. Let's say we go from 50 to 150. How does 45.5 compare to 211 or 411? So 411 divided by 45.7 comes out to be roughly 9. Again, it would be exactly 9 if we didn't have to round. So when I doubled the distance, I multiplied doubled the speed, I multiplied the distance times 4. When I tripled the speed, I took the stopping distance times 9. Now they didn't ask us to do this one, but let's do one more. What if we quadrupled the speed times 4? What did that do to the stopping distance? So we want to know how many times did the 45.7 get multiplied to get to 730. So 730.7 divided by 45.7 comes out to be roughly 16. So can you see a pattern here? When I doubled it, I took it times distance times 4. When I tripled the speed, I took the distance times 9. And when I quadrupled the speed, I took the distance times 16. Well, look at the relationship between these. 2 squared is 4. 3 squared is 9. 4 squared is 16. So what on earth do you think in this formula is causing this result to be a square of the initial input? Well, it's this number right here. So when you do anything, it's not just taking the distance times that, it's taking the distance times that squared. Because we take the initial velocity, the 50, the 100, the 150, 200, and we put it in here, and we square it. So what are some other questions you have about the relationship between speed and braking distance? So that's what happens here. If we double the speed, the distance gets taken times 4. If we triple the speed, the distance gets taken times 9. And basically, in general, the distance gets taken times the change in velocity squared. That's a little fancy math symbol for change. So the distance gets taken by the change in velocity squared. So however much you multiply that speed by, that initial velocity by, you're going to square that to get the change in the distance. Now, it asks, what are some other questions that you have about the relationship between speed and braking distance? I think we covered most everything that's needed here, but we're going to cover in the next lesson some different aspects of the formula. One thing that I do want to mention is these numbers over here were completely my choice to pick. I just picked some numbers that were easy to work with. But you could have had any numbers over here, as long as at some point you got 2 numbers that were doubled and 2 numbers that were tripled and 2 numbers that were, I went up to quadrupled even though they said tripled. So you just want some numbers that kind of go in a progression so that you can kind of see what's happening as you multiply these, what happens to these over here. So to conclude Unit 13, we're still talking about this same formula for the braking distance. And it asks, how could you explore the effect that different grades have on braking distance? And what they recommend here is keep the friction fixed at F equals 0.8 and then keep the same speed for your V naught. And we can use whatever we want for that. I'm going to go ahead and use the 66 that we used at the very beginning, but we could really use anything as long as we kept it fixed. So let's keep our V naught at 66. Let's keep our, and that was 45 miles per hour, was 66 feet per second. This 64.4 was our gravity. And then that was 2 times the acceleration due to gravity, 2 times 32.2. That's a constant. We're going to keep our F at 0.8. And then what we're going to do is we're going to choose some different G's so that we know how does the roadway grade affect the distance. So if I multiply this out and kind of simplify things, we've got 66 squared as 4,356. And we've got, again, this is 64.4, and then this is going to stay 0.8 plus G. I could distribute this, but it really doesn't help much because I still would have 2 calculations. So I'd have whatever this came out to be, and then I'd still have to do 64.4 times G. So I'm just going to leave it the way that it is. And I'm going to make a little table here, and I'm going to pick some different G's and see what happens to our stopping distance. So we already know that for 0.05, we have had that stopping distance of 79.6, I believe it was. Hopefully I'm right on that. And I'm going to put this in a progression. Remember that we said roadway grade could actually be negative numbers. So I'm going to start with one of the numbers that we had before, 0.3, and then we had 0.15, and then we had 0.05. That was the one that was 79.6. This is our stopping distance. And then I'm going to say, what if we have a roadway grade of 0? Because that would be flat ground. That would be not sloping up or down. And then what happens if we have a negative slope? What if we're going downhill? And I'll just do a couple here. We don't necessarily need to go up to 0.3. So if I kind of fill this in, I can kind of see as I go from sloping upward a good amount to not sloping quite as much, a little less slope, not sloping at all, being very flat, to actually going downhill. So this would be, again, this would be like uphill, uphill but not quite as much, uphill but not even quite as much. This would be flat. This would be going downhill a little bit, and this would be going downhill even more. So as we progress, we go from going uphill to going flat to going downhill. So if I take this number and I put it in here, for the first one, I would get 4,356 divided by 64.4, and then I'm going to put in 0.3, and we already calculated this, but I don't have it written down handily, so it'll be easy, just as easy to recalculate it. So 4,356 divided by 64.4. We have to be careful on this. You have to use, you actually have to calculate this first before you divide, or you could end up with an error. So if I want to calculate this all in one step, I can. I could do 4,356 divided by parentheses 64.4 times parentheses 0.8 plus 0.3 parentheses. I think that leads to the possibility or the potential of more errors. So what I would recommend is just calculate this bottom number and then divide. So the bottom number, if you calculate 64.4 times parentheses 0.8 plus 0.3, which you could calculate first and then multiply, that comes out to be 70.84. So it's 4,356 divided by 70.84. Which comes out to be around 61.5 feet. And again, we had calculated that in a prior lesson, but we'll recalculate it here. Now here, we're going to put in 0.15. So we're going to do the same calculation, but instead of putting in 0.3, I'm going to put in 0.15, which is going to change this bottom number, and recalculate that. So this will come out to be, on the bottom, 64.4 times parentheses 0.8 plus 0.15, or you could put 0.95, and that number on the bottom comes out to be 61.18. Now that's not our number yet because we now have to divide to get this number. So 4,356 divided by 61.18, and we get roughly 71.2. So this goes, when I cut this in half, it goes the distance, so it's not as steep, and so the distance goes up. It goes up by 10. Here it goes up by 8. Now what happens if we put a 0 in there? So taking this formula, again, taking out this number that we have here, this 0.15, and replacing it with 0, what does that do to our calculation? So this is going to be 0 now. and 64.4 times 0.8 comes out to be 51.52. And now if I divide 4356 divided by 51.52, we get about 84.5. So from here to here, we go up 10, up 8, up 5. So you notice we're not gaining as much distance by decreasing the slope as you think you might, because this got cut in half, and then this got cut in a third, and then this got, completely reduced to 0. So now what happens if we put in a negative 0.05? What's that going to do? And again, this means that you're trying to stop going downhill. So this would be negative 0.05, which I'm going to do an extra step here. That'd be 64.4. If I add these together, that actually ends up being 0.75, because it's like taking 0.8 and subtracting 0.05. So 64.4 times 0.75, we get 48.3. So 4356 divided by 48.3, and we get a stopping distance of about 90.2. So difference from here, we go up 10 extra feet, up 8 extra feet, up 5 extra feet, and I'm just estimating here. And then from here to here, we have roughly almost 5 again. So from here to here, from 0.05 to 0 and 0 to negative 0.05 is similar. In fact, I think it's the same. Let me double check. So 84.5 minus 79.6, we get 4.9. I guess it's not the same, because 90.2 minus 84.5 is 5.7. So it is a different number. And so now we're going to do that very last calculation of going to negative 0.15. And so if I put in negative 0.15 here, that's going to put me at, instead of 0.75, that's going to put me at 0.65, because that's like 80 cents minus 15 cents. You'd only be at 65 cents. So this would be 65. And if I take 64.4 times 0.65, I get 41.86. And that's what we're going to divide by. 4356 divided by 41.86, and we get 104.0. And again, that's 3 times rather than just doubling it like we're here. So seems like it should be quite a bit of a difference, but it really only adds about 14 feet to your stopping distance, not quite. So as the biggest thing here is, as the grade goes downward, whether it goes all the way from a upward slope to going downhill, that's going to increase your stopping distance. And that is because this G is on the bottom. So if we have a smaller number, it's going to divide in more times and give us a bigger distance. So just to conclude, they want to remind us that in this lesson we've used several formulas now, and we developed spreadsheet formulas in the earlier lessons. So And then in Lesson 11, we used geometric formulas. In Lesson 12, we looked at our own formula to analyze Jenna's driving costs. So what we're trying to work at here is understanding and knowing how to use variables, including, like in this case with the v, the subscripts. So v sub naught doesn't mean it's two variables or anything. It's just indicating which velocity it is. Understanding and knowing how to use the order of operations, and understanding and knowing how to use units, including the dimensional analysis. And with those skills, you should be able to use basic formulas of any type that you run across, whether you're in the medical field or the arts or the culinary field. Any of those things, if you know those basic things about how to put in a variable and what a subscript means and how to follow those order of operations and do dimensional analysis to change units, you should be able to use most basic formulas. So that concludes Unit 13, and we'll pick up next week with Unit 14.